gone through screening for our independent sample t-test. Anybody remember if we found anything too concerning with respect to our independent sample T's? We don't remember anything. I remember nothing. Okay. What's that?
Terrible.
Nothing terrible. And you're right. You would be correct. We didn't find anything super screwy. What was the big thing that did come up with this screening that would probably be the biggest pause in terms of thinking about impact on our inferences?
We only had 4 girls, right?
Yeah, we had 5 dudes in this sample, right? We're doing a gender differences in marital satisfaction and what was the other thing we're looking at? Marlowe Crown stuff, social desirability. Okay, and so even though in terms of we're thinking about our distribution of sample means, thinking about whether or not we have weird outliers or things like that, none of that looked like it was too big of a deal. The one thing though that we did take notice of was that we have an unbalanced design, and that even among our women, so we have 21 women, I think, and 21 women and like 5 guys, that starts to become difficult. That starts to cause us some concern with stuff. Yeah, 21 men, or excuse me, 21 women and 5 men. Okay. So we want to go through, make sure we noticed someone. If you want to open up this data set, we'd also found one person, a woman who had been missing data, so we got rid of that person, but outside of that, everything was looking fine, okay? So, after all that, what we're ready to do is we're ready to jump in and actually run our statistical test here. So, again, we're working with the independent sample T handout that I gave you here, so make sure you pull that if you want to take notes or anything. And so what we're going to do is we've gone through and we've screened, and so we're going to go to Analyze, down to Compare Means. We're going to go Independent Sample T-Test. Click that, and we're going to be looking at our Locke-Wallace marital adjustment and our Marlowe Crown. Okay. And then our grouping variable is going to be gender, so we're going to drop this down. And then for our grouping variable, now in SPSS we can run t-tests. Let's say I'm looking at, Chris, you've got a manipulation where you've got 4 different conditions, right? We can still run our t-test even though your grouping variable has 4 different conditions. All we need to do is we need to drop down and hit define groups, and we just need to tell it what numerical values we want to that we want to compare. So here, our women, our men, our group 1, women, our group 2. Go through and hit that. Up here, we can have options. You can change your confidence level if you want. We don't want to do that, really. So we'll go through and hit paste. Once you have a handle, you've done some of these, you can just start working within your syntax file. You can see it's pretty easy. Here's your grouping variable, here's your dependent variables. It's not too difficult to go through and work with that. So we're going to run this. All right. And this is what we get. So looking at our output, up here, we've got our descriptives table, right? Always, always, always go through and check your descriptives to make sure that SPSS is looking at what it is that you want it to look at. So we see for both the Locke-Wallace and Marlowe Crown, we have 5 men, 21 women. That's consistent with our screening, so we're looking good there. We're looking at means and standard deviations. All of those look reasonable, right? Consistent with what we would expect. So this is just good policy to always check that first and make sure everything looks kosher before we move forward with things, okay? Now, down here we get our independent sample t-test. First thing we'll notice is we've got 2 different rows. We've got equal variances assumed and equal variances not assumed. Okay? Siley, if we're thinking back into a assumptions of our independent sample t-test. Do you remember what these two rows might be referring to here? Yeah. This is our homogeneity of variance assumption, right? We don't get it in our screening, but it will pull it up for us in SPSS here. This is our Levine's test, okay? And our Levine's test is going to go through and it's going to let us know whether or not we have evidence of a violation of a homogeneity of variance assumption here. And tomorrow, and again, this is asking to go back from last week, but for our marital satisfaction, does it look like we have a violation of homogeneity of variance here? You don't know?
For the lock walls.
For the lock walls, yeah. Doesn't look like it, no. And how did you determine that?
It's not 2.05 or less.
Exactly. It's not statistically significant. This is one of these tests where we're pulling for a null effect, right? We don't want to see evidence of a statistically reliable effect, because if we do, and again, remember that any time we have some sort of statistical test, it almost always means that something's equal to 0, right? And in this case, if we're looking at the difference in our variances, we want that to be 0 or-ish, right? And so if we look at our Levine's test here, find very little evidence of or strong indication of violation of a homogeneity variance assumption, right? So we can go through and we can read off of this line equal variances assumed, okay? So we go through, we have our t-statistic, our degrees of freedom, our p-value here, and then we've got our mean difference, standard error, that difference score, and then our upper and lower confidence intervals for this. So Nick, what if we're looking at our confidence intervals, what does our confidence interval tell us here?
That the mean difference between men and women is going to be on the negative side in terms of men being less, but it's anywhere between 54, negative 54 and negative 2, which is pretty wide.
Yeah, right. So it's pretty right because we've got really, really small samples, right? And so what this is saying, the population of car accident survivors, at least based on the data that we've collected, we're saying the difference in marital satisfaction that's across men with PTSD and women with PTSD. Looks like men are lower, but that difference could be anywhere from 2.5 points lower in marital satisfaction to about close to 55 points lower, right? And if we're looking at variation in the lock walls across men and women, again, our Levine's test is saying that these are standard deviations. We want to be careful. If we were to go through, so we've got about a 5-point difference in terms of the standard deviations. What happens if we square those and look at the difference? It's going to make it bigger, right? So if I go through and I take 30.4 squared and 24.4 squared. So we've got about a 25-point difference in the standard deviations, but a 328-point difference in the variances, right? So remember that any time we're squaring anything, it makes it a lot bigger. And so that's what we're testing, is differences in the variances, not the standard deviations. But overall, in terms of variance estimates, it looks like these two things are at least similar. But if I look at that 2-point difference, right, what ends up actually being the upper limit on my confidence interval, it says the difference in marital satisfaction could be anywhere, could be as low as a 2.5-point difference. So CJ, is a 2.5-point difference likely meaningful on this scale, just given the variability across men and women?
Probably not.
Probably not, right? It's probably trivial. Now, for this question, we didn't say, oh, this is a meaningful difference, but just looking at the data, it looks like a 2.5-point difference is probably something that's negligible in terms of outcome, right? But on the other hand, 55-point difference, well, that's over a standard deviation, right? And so that's probably likely. And so in terms of meaningful impact, we have some ambiguity here, similar to the same situation we had with the set, the score in the problem set. Now, if we're going through and we're looking at our p-value, we are seeing something that we would say, yes, this is statistically different based on our conventional rules, but in terms of sort of whether or not this is a practical difference or sort of the strength of evidence against the null hypotheses is maybe a little bit more questionable here. All right, what other things can we do to go through and start to calculate and make a determination on whether or not what we have is thinking about magnitude of effects? What else can we calculate? Effect size, right? And so for these data, we talked about one of the tricky things in choosing for our independent sample t-test is choosing an effect size to calculate, right? Anybody remember some of our options for this? Hedges G. Okay, so we could pool this. We could pool the variances across these two. That's a possibility. What are some other options? Cohen's D. Okay, and Cohen's D is sort of like our baseline, right? Cohen's D just says the difference across the two means divided by a standard deviation. Cohen doesn't specify which standard deviation. And so Cohen's is kind of tricky because I could use this or I could use this. Chrissy, which one am I more likely to want to use?
The smaller one.
Yeah, the smaller one. Probably women, right? Like, oh, well, they're the same. I'll just use the standard deviation for women. What's going to make my effect size incrementally larger, right? And so this is where Hedges comes in. If we go through and we just use our pooled variance, then we don't have to worry about sort of choosing which one. Okay. What about Glass's delta? Did anybody ever remember what Glass's delta was talking about? Okay. Here with Glass's, we choose one, but which one? When is it advantageous to choose one standard deviation versus the other? Remember?
You choose the standard deviation from the larger sample, whichever group is larger.
We could, and that would be if we assume that, and that's actually, if you wanted to make a case for just using one of them, right? You could make an argument for, well, we're seeing that we're not finding evidence that they're different. And so what I'm going to use is I'm going to use the larger one because that's likely the more precise estimate, right? But with Glasses, remember, with Glasses is where we're using a baseline, or if you have a control, right? Because this is nice because then we can say, all right, this is variability in its natural state. This is where people are at when they come in, right? And so, or this is sort of the variability that we see in some outcome in the absence of manipulation or intervention or things along those lines. And so Glasses can be nice if I'm sort of comparing this group that's watching a test pattern of sort of whatever, and this group that's actually getting a manipulation, right? But do we, in this case, have a good baseline or so like a control? No, not really. We've got men, we've got women. And so probably what I'm going to do is calculate a pooled variance estimate using a Hedges G. But what's the other thing that we had talked about that we might want to go through and address in this question here in terms of effect size?
Hedges unbiased, G?
Yeah, why is that?
Because it's a pretty small sample.
Because it's a pretty small sample. We know that with small samples, our estimate of effect size is probably too big, right? And so what we can do with Hedges is we can go through and we can institute a correction. So what I'm going to do for my, so what I'm going to start is I'm going to start with the calculation of a pooled variance estimate. Okay. So remember what we're going to do with our pooled variance estimate. It's going to be n minus 1 times variance 1 plus n minus 1 for my second sample, times variance for my second sample, all over n1 plus n2 minus 2. Laura, I'm sorry, I need to get my act together. Would you grab? You just tell me, like on the front end, like, hey dummy, go get down your markers. Okay, so if we go through and we plug this in, we're going to have 4. So we got 5 guys in our male sample, And here, we're gonna take, just from our output, 30.366, or we're gonna square that, right? Alicia, why did I square that value?
Make it larger.
If I square this value, what does it turn it into? This is my standard deviation. I square my standard deviation, what do I get? Variance, yeah. If you take the average variance and you take the average standard deviation, those are not the same two numbers. That will turn you around, okay? So you always want to make sure we're working with variance estimates, okay? So we're going to go through add 20, which is our second sample, or size of our female sample, minus 1, 24.415 squared, and take this over, which is basically our degrees of freedom, which is going to be 24. Okay, so we got 21 plus 5 minus 2, 24. Gives me a variance estimate here, 650.426. Is that consistent with what people calculated? You get that, Chris?
I got a different number.
Okay, so make sure that you're squaring your standard deviations first to get your variance estimates, and then multiplying those by sample size.
Let's divide by 24. Okay, yeah, we're on the same page.
Okay, cool. It's always good to check my math. Sometimes off. Okay, so this is my pooled variance. Is this what I will need to calculate my standard or my effect size?
No, I got the square root.
Gotta take the square root. So here, take the square root of this, I get 25.503, and this is my pooled standard deviation. Okay, and so again, if we take a look at our pooled standard deviation relative to what we had used for our men and our women, CJ, which for men and women, where's this closer?
Women?
Women, yeah, why?
Larger?
Yeah, because they have more people. There's more. The sample for that is bigger, right? So we were weighting our female sample heavier in the calculation of my pooled variance estimate because we were assuming that that's a more accurate estimate, right? And so it's getting weighted heavier. And so we see that our pooled standard deviation looking more like the variability that we're seeing among women than we're seeing among men. Okay. So we've got our pooled variance estimate, or our pooled standard deviation. So hedges G is just going to be, we go up and take a look. Difference is 28.644. Divided by 25.503 is the hedges G of 1.12. Nick, can you give me a conceptual interpretation of that effect size?
That is a large effect size.
It's a large effect size, good. Can you get a little more specific?
Yeah, it's just over one standard deviation
Okay,
between the two groups.
okay, cool. So we can go through, and this starts to become more meaningful if we're sort of giving it, sort of like actually labeling what's going on. Here, I would say that based on the data that we've collected, our data is suggesting that men are scoring about a little over a standard deviation below women in terms of marital satisfaction, right? And that's actually kind of a big deal, right? Our effect size is saying that this is not a trivial effect, that it's actually quite large, right? And specifically, we're seeing men scoring, or women, if we want to flip it in marital satisfaction than men, right? And so we're kind of getting different conflicting information, right? We talked about the low end of our confidence interval suggesting something trivial. The high end of our confidence interval consider looking at something that could be quite large. Our effect size for the point estimate is suggesting a large effect, right? We could also go through and we could calculate S values and base factor here. S is going to be the natural log of 0.033 or the natural log of 2. Absolute value of that. That gives me an S value of 5. My base factor bound is going to equal 1 over 2.17 times 0.033 times natural log of 0.033. Okay, it's going to give me a base factor bound of 3.27.
So when reporting S values, do you want us to round to the nearest whole
Yep,
number?
yep. For S values, you're rounding up, rounding the nearest whole number, right? Because again, the idea is that S value is giving you bits of information, right? So this is, I can't have like a half heads if I'm flipping a coin, right? So we're gonna round up there. So what we end up with in this situation is really some ambiguities in what our data are telling us, and that's fine, right? Based on the data that we've collected here, we were expecting women to report higher levels of satisfaction than men. And that's sort of what our data are kind of alluding to. And in actual fact, it's associated with quite a large, they got about halfway there. We're going to use unbiased, right? So my unbiased G is going to be 1.123 times 1 minus 3 over 4 times 5 plus 21 minus 2 minus 1. This is just our correction value, right? So I get a hedges unbiased here of 1.087. Okay, so I went from so the correction isn't huge, right? I went from 1.123 to 1.087. It's still saying that the data that I've collected here is suggesting a substantial reduction in terms of standard deviation units, right? But when I'm actually looking at the strength of my evidence against the null hypotheses, right? My problem here, we've noticed this from the beginning, is I've got a really small sample, right? Now a p-value is less than the traditional 0.05 threshold, but if I'm looking at my sort of associated S value here, right? Basically it's saying that these data are giving me about the same evidence against the null as I would expect from getting 5 heads in a row from a fair coin. Now, if I get 5 heads in a row, am I going to start to suspect that Nick is not giving me a fair coin to toss? I might suspect it, right? It's not a super high probability event, but it's not outside the realm of possibility, right? There are certainly worse bets that you can make other than getting 5 heads in a row, right? And so it's suggesting that there's maybe something there. Again, base factor is 3.27, right? So saying that based on the data that we've collected, in the best case scenario, that the alternate is about 3.2 times more likely than the null, which is okay. If we go back through, I sent that email out about estimates on Bayes bound. DJ asked me about that. He's like, "Oh, did you have a good Saturday?" What did you hear? I don't know. I forgot that I had done that, which I forget lots of things. That doesn't say anything about anything, but,
So you did have a fun Saturday.
right, yeah. But if we're thinking about, you know, those rough guidelines, this just kind of tips over into like strong evidence, right? And so at the end of the day, I think this is one of these examples where I would, if these were my data, I would sort of reasonably say, yeah, it looks like these data are consistent with my hypotheses, and hopefully I have a good conceptualization for why I would expect this, sort of based on theory and things along those lines. But I would probably be hesitant, right? If you asked me if I was, how confident I was that these results would replicate if we were to get a bigger sample, maybe, right? I'm not super strong. Like, would I stake my career on this result? Absolutely not, right? So this is where I think we started getting this tension between, like, no one's asking you to crap on your own results, and if you found it within the context of our publishing system, I can claim this as a significant result. But if I'm being responsible about this, and even if it's just me being responsible in my own head, I should be looking at this as the basis for anything else I'm going to do. I was like, well, I mean, the really differences that here should be trivial, right? If this is going to be my basis for going out and collecting and doing a whole big couple relationships thing based on this finding, I'd maybe pump the brakes on that a little bit, get something a little bit more, something I can be more confident in before I start moving forward into investing resources and everything into this big program based on this research. Okay. Questions about any of the interpretations, any of the stuff that we've done here? So again, in my interpretation of these results, I would say, yeah, it looks like there may be, or there data are suggesting some evidence for differences in marital satisfaction with men reporting lower levels of satisfaction than women. However, if I'm looking at my confidence interval, the upper end of my confidence interval suggests that reduction may be relatively trivial. My S values, my base factors, and that I have some evidence, but it's not terribly strong evidence, right? And again, that base factor is based on the ultimate, like, best case perfect scenario. Is this likely the best case perfect scenario? Probably not, right? And so wanting to take that into consideration when we're evaluating our own research and research of other people. Questions on any of this? All right, cool. Other thing we're looking at here is, and the way we'd set this up is this idea of, well, maybe if I do see a difference, maybe it's just that men and women are different in terms of their social desirability. Maybe women are just less inclined to report low satisfaction than men. So maybe we should go through and think about that, right? Alicia, when we're looking at our Levine's test for for Marlowe Crown, what are we seeing here?
A big difference from the Wallace.
True. Should I, what might I conclude about potential violations of homogeneity of variance based on my Levine's test here? Have I violated homogeneity of variance or not?
Yes.
Maybe. So if I'm just basing it on the test, right? Hard cut value, 0.05. Do I have a violation or not? Do we want Levine's test to be significant or not significant? Not significant, right? Is 0.054 technically significant? No. So technically, if we want to just say, here's the thing, then I would say that no, I haven't violated homogeneity of variance, right? But this is a statistical test, just like any other statistical test. And what do I know about the power of a statistical test based on sample size? Chris?
Certain by sample size.
Certain by sample size. So is my Levine's test very powerful?
No.
No, it's not, right? I'm comparing a sample of 21 to a sample of 5, right? And so if I'm actually looking at my variances here, I've got a difference of 16 here-ish, if we square that, and 49-ish, so it's up there, right? And that's actually pretty big, right? So if I'm looking at this, if I want to just say yes, no, I can say, no, I have violated homogeneity variance because that's not less than 0.05. But if I'm looking within the context of my study, I'm expecting that Levine's test to be not terribly powerful. And so I might say, this is enough for me to say, okay, I'm not going to assume equal variances in terms of this test. Now for Marlowe-Crown, it doesn't make a difference, right? If I look at equal variances assumed, equal variances not assumed, my means are almost identical across across men and women. There's nothing to see here in terms of at least these data. That's not saying that men and women don't differ in terms of social desirability. I'm just saying that these data don't give us any indication that, at least in this case, that we can treat these as at all difference, right? And so this helps rule out the possibility that differences I'm seeing up here are driven by just responding style and things like that, right? But we'll see here with relative to my t-test is different, right? And this is based on that Welch-Satterwith correction. We see correction in my t-test, correction in my standard or in my degrees of freedom. But if I'm looking down here, we get a slightly different confidence interval. Mean difference is the same, but if I have a clear violation of homogeneity of variance, this is the row that I should be reading off here. Okay, but also remember, so here we have low power, and so we're questioning sort of whether or not we sort of give a little bit of wiggle room. If we say, have we violated the homogeneity of variance? Well, yes, no. Well, it's not a yes/no question. Like anything else, it's a continuum, right? We can violate it by a whole lot, or sort of not at all, or somewhere in between, right? This is kind of giving us general rules by which to think about things, right? Well, what happens, CJ, if, let's say I have 300 men and 400 women, and then I go through and I find that this Levine's test is statistically significant? Why might that give me pause for concluding that I have a violation of homogeneity of variance?
There's a pretty good amount of power.
Yeah, right. And so my concern is that any difference in variability, even trivially smaller differences in variability, could pop up as statistically significant. Now, if I've got that many people, the difference between in terms of my conclusions based on equal variances assumed or equal variances not assumed, it's gonna be trivial. It's not gonna make a difference, right? So it really, at that point, it doesn't matter, right? But always wanting to think about, this is the same reason we don't interpret indices of skew and kurtosis and whether or not they're statistically significant or not, because that's all driven by sort of the power of your sample, and the assumption is that our skew and kurtosis is zero, and we don't care about that, right? But again, going back to our marital satisfaction, if we're looking at equal variances assumed and equal variances not assumed, is there anything there that might cause me pause, give me pause in terms of making a strong interpretation about average differences? What do you think, Tamara? Yeah, so if I were to assume that equal variances, if equal variances were not assumed, what would my test statistic tell me?
It's still not significant.
Oh, yeah, for Locke-Wallace.
Oh.
I'm sorry, I wasn't clear.
Yeah, that, it would no longer be significant.
Right,
If
and
the variance was significant.
exactly, right? And so again, this is something to be thinking about, right? Now, there are arguments, and Hal makes this argument that, you know, we should always just always use equal variances, not assume, then don't worry about it, right? I mean, there are people who advocate for that position. But if I'm looking at my Locke-Wallace scores, if I assume equal variances, I've got a p-value of 0.033. If I don't assume equal variances, now all of a sudden my effect goes away, right? That should make me nervous about stuff, right? Now this is things that only I see because I'm the only one who's doing my stuff. But again, if I'm thinking carefully and being realistic about the stability of my effect, if this makes that much of a difference, I should probably be cautious in how I'm interpreting this, right? Technically, by the rules of the game, you can say, yeah, we found this effect, and it is based on these data, It's based, associated with a large effect size, but at the end of the day, if I'm thinking about replicability and sort of whether or not this is actually capturing something that's going on, or the precision of my point estimates here, I need to be probably careful, at least realistic in my own head. What you project out in the world is up to you, but I should probably be cautious in terms of interpreting this stuff. Does this make sense? Any questions on any of this stuff? Yeah?
This might be a really, like, an oversight on my end.
No.
But for the equal variances not assumed.
Yeah.
Why is the, like, degrees of freedom different?
Okay, yeah, why is the degree of freedom difference? Anybody remember what we're doing with Welch satellite correction? Remember that the idea behind, so I don't expect it, that would be, it would be impressive if anybody sort of pulled that from last lecture, why we talked about it, but remember that our assumption of our independent sample t-test is that we have equal variances, right? And if we have equal variances, then the test statistic that we would get the sampling distribution of our t follows our expected t distribution with associated degrees of freedom, right? But if we have violations of homogeneity of variance, all of a sudden the test statistic that I'm getting when I'm comparing sample or populations that don't have equal variance, the distribution of that test statistic doesn't map on exactly to the test statistic or the distribution that we expect, right? So if we had violated homogeneity of variance here, this t statistic not distributed as a t statistic with 24 degrees of freedom. The Welch-Satterthwaite assumption is that test statistic still is, the sampling distribution of that still is following a t distribution. It's just not the distribution with 24 degrees of freedom. And so what ends up happening is we go down through this correction, we get a correction in the t, and then a correction in the degrees of freedom, right? So this is saying, based on the available data that we have, the sample size, the variances that we've seen, then we're saying that this is a test statistic of 1.96 that follows in the sampling distribution of this test statistic, follows its sampling distribution of t with 5.3 degrees of freedom.
Can we have, like, degrees of freedom though?
Mathematically, you can. If you're looking in your t-table, there's not decimal degrees of freedom. Mathematically, you can calculate this. When we get into post hoc tests for ANOVA, I'll throw you a calculator, which if you, in like the graph pad thing that you guys have been using, if you try and enter a decimal, it won't let you do that. But there are other online calculators that let you specify decimal degrees of freedom if you're looking for critical values and things like that. So that was an excellent question. Again, it gets at this basic reason why we're looking at assumptions, right? If these things are true, then our test statistic behaves in this way, it follows this distribution, and we can assign specific probability values to data that we've observed. But as soon as we start to violate those assumptions, now all of a sudden the distribution of our test statistic doesn't follow the distribution that we think it does, and so that starts to bring into question all of our inferences and probability values and decisions and things along those lines. Other questions about any of this? Okay. So, and then, you know, if we want to calculate effect sizes for Block-Wallace, we could do that. I won't do it by hand, but have a handy dandy calculator here that will do it. Here's my independent sample t-test. So if I've got for the Marlowe Crown, I've got group 1 has a mean of 18.6, and a sample 2, 18.857, standard deviation group 1, 6.804, 2, 4.1, 2. I've got 5 people in this group and 21 people in this group. Looks like my unbiased G here, you guys probably can't see that, but negative 0.053, so it's trivially small. So it's like 5/100ths of a standard deviation difference, right? Suggesting that there's nothing much going on there. And the same thing, I can go through plugging my S values and things like that. Okay. So, marital satisfaction stuff. Okay, we can go through, calculate our null, our alternative, our 95% confidence intervals, effect sizes, hypotheses tests, S values, base factor, interpretations. This is what things are looking like in SPSS. This is our output that we just worked through. Alicia, for people using Stata, what we're going to do here is we've got, instead of running your Levine's test within the actual test statistic, what you're going to do is you're just going to hit use this command, enter your outcome by gender, and then this is just your Levine's test here. So you just type that in, run your Levine's test, take a look at that. You'll see that the values are identical to what we saw in SPSS. And then if we go through, run our independent sample test, just t-test your DV by your gender, and then depending on whether or not you want to run equal variances or not equal variances. Unequal, it just gives you unequal variances. If you leave that off, it gives you equal variances. So going down through, running the same thing. Here's your sort of difference, here's your test statistic, here's your p-value for your two-tailed tests, basically all the same stuff that we did with SPSS. And I put those on those online videos walking through all of these, so it should be pretty straightforward and easy. Other thing we can do in Stata that's nice, that will give you an advantage because you're using a different program than everybody else, which kind of sucks. But one thing you can do is this will, within the program, eSize 2 sample will give you all of your effect sizes and also 95% confidence intervals for your effect sizes, which SPSS will not do, right? So your Cohen's D, this is actually Hedges G. This is just using your pooled variance, right? Hedges G, what Stata lists as Hedges G is actually your Hedges unbiased G. So this is just with the correction. Glasses Delta 1, this is just using the group 1 as your, as the standard deviation. 1 is your standardizer. Delta 2 is just using the other group's standard deviation as your standardizer. And then this one by series, you don't have to worry about that at all. That is to this. So this is nice. You can go through and just plug yours in and pop up your effect sizes automatically within the program now. Effect size 95% confidence intervals in Stata, right? Or in SPSS. The desert wasteland out there. This is a professor at the University of Vermont who also teaches statistics, but fine. This is where we are with SPSS. Statisticians don't think much of SPSS. It's not as bad as they make it seem. The way you t-test in your program is no different than t-test in anybody else's program. Ours is kind of a no man's land of stuff, but all right. Here, example writing. Okay. Now again, if we're looking at this, this is a lot of stuff. This is just me going through providing an example of how we might go through and put this together. So this isn't, you don't have to put this in your write-ups if you don't want to. This is all covered in your screening, right? And we go through and we pull the handout that I gave you for in-class example for the independent sample screening here. Again, we noticed that we were missing one score, Marlowe, Crown, and Lock Walls for case number 132, which was one of our female participants. No problematic values, finished with a 724. Skew kurtosis distributions for men, skew kurtosis distributions for women, outliers, homogeneity of variance based on our Levine's test, and then just recommendations down here in the bottom, right? So this is a nice way to just kind of go through and bullet your screenings with this next set. You're going to have to go through and run these screenings. Please, this is what I want it to look like in terms of bulleting things out. This is what you might need to do in terms of something that looks along this. This is more intense than you would need to do for a publication, but for the purposes of our class, just going through and structuring so that we can go through and pick things out to use this as a general framework template stuff. So taking a look at that. But here, this is me trying to pack in the stuff from this example into something that sort of communicates what we have, what we don't have, right? So We say Marlowe Crown failed to provide strong evidence of differences in socially desirable responding, right? So I'm putting my mean standard deviation, mean difference, and then my confidence intervals. This is me communicating to whoever's reading this. It's not just me saying that there's nothing, like you can look at the numbers yourself. There's really not much there. Independent sample t-tests identify data is generally compatible with null or near null differences, assuming the underlying model. Here's my test statistic, my p-value, my unbiased G. So once we've done that, we're kind of done with that. I mean, there's no sense in continuing to talk more and more about stuff that's clearly not sort of different, right? But we say potential for greater marital satisfaction in female survivors with point estimate of unbiased G, indicating a full standard deviation increase among women as compared to men. Then we're saying confidence bounds range from difference about 2.5 to about 55 as plausible estimates for the true difference across populations. Worth noting that lower bounds supported by these likely not consistent with meaningful differences, right? If we're looking at the variability in a Lock-Wallace scores, if we're looking at sort of where that is in terms of a difference of 2.5 points, that's about 8/100ths to about 1/10 of a standard deviation difference. Independent samples t-test also provides only modest evidence for an absolute difference in satisfaction. Bayes factor bound says that the alternate hypothesis is at most 3.3 times that of no difference across populations. And then here this is just sort of extra stuff I'm sort of going through, including sort of posterior probabilities and things like that, just to give you an example of what that might look like. You don't have, Chris had asked, do you need to put all that stuff into your calculators for this set? You don't have to if you don't want to. If you want to, it's not too hard to program in there, but this is just an example of how you might incorporate some of that other stuff into a meaningful interpretation. And so in conclusions, we suggest a possibility of greater marital satisfaction among women as opposed to men, although strong conclusions regarding the magnitude and generalizability of this discrepancy require further study, right? So again, trying to say, yeah, it looks like, based on these data that we've got, it looks like there could be something there, right? It looks like maybe there's not nothing, but in terms of the magnitude of effect, replicability, really need to have more sort of stuff going on before we would start to make strong conclusions about this difference, okay? Now again, in terms of your own stuff, remembering that this is all within the context of existing research, right? So Alicia, if you've gone through and there's study after study after study after study, right? There's like 10 different studies that find that yes, there is this very clear difference, and this is something that comes up again and again and again and again. Does that change my conclusions based on what I found here? Yeah, you're nodding your head, CJ, why?
Because you have more confidence when you found.
Yeah, right. If this is something that people have consistently found over and over again, then it puts some of this stuff into context, right? You can say, well, my super wide confidence interval around this effect, it actually kind of falls in with what people have found. This individual study is kind of pretty limited in terms of sort of if it was on its own thing, but within the context of people having found this again and again and again and again, this is just a small sample example of sort of me finding the same thing that other people have found, right? But Alicia, if no one else has ever looked at this before, this is something that we can't find good evidence for existing in the context of past research. Now all of a sudden I need to be much more careful in terms of the likelihood that tomorrow is going to replicate or Saturn's going to replicate or something along those lines. So again, thinking about taking context into account when we're going through drawing conclusions from our data. All right, questions on any of this stuff? Yeah.
Why don't you just recruit like 10 more people?
Yeah, right. I mean, well, and this is, and that's probably what would happen if you were trying to publish this. This is probably not publishable, right?
Let's say it gets equals.
Right. And in our history, this is something that definitely might have been publishable in the not that deep recent past, right? But it's also possible, and particularly for us clinical folks who are doing stuff, if it's possible that maybe these are all the people that I could get. If I'm working with something that really doesn't happen a whole lot, and these are all the people that I could get, that might come into play in terms of me as a reviewer evaluating this. Like, well, yeah, that sample kind of sucks and it really limits what we can infer, but you find me someone else who's got sort of this group of people done this stuff, right? And then you can start to make arguments, and this is the thing that you need to be thinking about in terms of making arguments for your research, right? This is a strong argument. If this is undergraduates in sort of just a general sort of lab study, yeah, you need way more people. Give me a break. Get out of here with this, right? But if you're actually sort of working with, and it took, let's say there's like an MRI study or something like that, then each person who comes through costs me thousands and thousands of dollars to run, and I kind of tapped out my grant stuff, and this is what I've got, then, then I might say, I know it's not the strongest evidence, but given this method, it's the best thing that we have, and so making arguments there. And I think to do that, this is sort of clearly not a great sample, but it's enough to sort of start to hopefully sort of outline some of the ambiguities that we can get in terms of our research and sort of seeing some of the limitations of just making yes/no decisions based on whether or not we tip on one side or the other, 0.05. Other questions? Okay, cool. This might be where you might write up in a publication, just kind of condensing this all down, something a little bit more efficient. But that gives us independent sample t-tests. Let's do this. Let's have a break. We'll come back and finish up with repeated measure stuff. We'll test, retest, calibrate them and see if that's any good. So if we're thinking about our repeated measures, what we're doing is we're taking the same group of participants and we're evaluating these on these individuals on one or more or two or more occasions. Okay. Now we've got an asterisk here. Anybody. So if we think about a traditional repeated measure design, we're saying same group of people measuring on two or more occasions. Why might I asterisk that? Any ideas? What other things? When else can we use a repeated measure to design? Yeah.
Oh, actually, I might have preemptively raised my hand.
Okay. Never mind.
Yeah, no, let me try. You can measure them, like if you have them in one study visit, you can measure them throughout the course of that study visit. That still counts.
Yeah, it's still sort of going through matched the designs, right? Technically, if I've got this group and I sort of match this other group based on sort of X number of characteristics, you'll see at the low end, so I've got these, this group of men and women with these characteristics matched with this group of men and women matched on the same characteristics. People will historically use that matched design and evaluate those in a repeat measure sample. So I've got Nick, and then I've got fake Nick, I've got Chris and fake Chris, sort of going through and comparing these, and then Alicia and fake Alicia, matched on all these characteristics, age, gender, so whatever relevant background characteristics, and then I'm pairing you and fake you in terms of a design and using that as a matched design. More elaborate are propensity matching scores, algorithms, and things like that. This is some big data stuff. Actually, we're working with a Census Bureau data set, or will be, that we're sort of going to go through and take people who've been exposed to violent crime and match them based on sort of 1,000 different things with people who are from the same region and sort of the same type of thing and are matched on this stuff, and sort of kind of using some of that. But in general, 99.9% of the time when we're talking about a repeat measures design, we're looking at sort of the same group of people assessed on more than one occasion. What's nice about this is this type of thing maps onto a lot of the types of phenomena we're interested in looking at. Learning, performance types of outcomes, shift in behaviors and motivations and things along those lines. I've got you here, I do something too, and then look at the impact on your motivation or your scores or things along these lines. A much more efficient use of resources, okay? Instead of having to get sample 1 of 80 people and then my control of 80 people, if I can just get one group of 80 people and just do whatever I need to do and sort of follow that along, much more efficient use of resources, and it helps me go through and ultimately reduce random error and sort of individual difference types of things, right? So Siley is really aggressive when she's a really angry person. When she's filling out sort of any type of self-report measure, there's a ton of negative affect going on that's influencing her scores, right? Chris, on the other hand, is a joyful person. He's a very happy, optimistic person. Sort of downplays some of the negative affect and things like that, right? If I go through and I have you two in just a twin groups design, and then I have Tamara and Alicia sort of in another group, like all the individual differences in how you approach that measure gets chalked up into random individual different stuff, and it makes things start to get really, really messy. But if I can have all 4 of you in a repeated measures design, right? So you're your own control, right? So even though you tend to rate things negatively in this time, I'm assuming that sort of tendency is going to follow you on in the next time, and so it starts to control for those individual differences. Same thing, Chris rates everything sort of maybe too positively. We assess him the second time, he still rates everything too positively. Your scores, your raw scores might be very different, but if you've changed all in the same direction, your scores are going to be pretty close to one another, right? And so what these repeated measures designed to do is they go down through and reduce some of that individual difference variability, makes for a much, much, much more powerful design. The most basic example of our repeated measures design, they get far more elaborate than this, but our paired sample t-test. What we're doing is we're examining change scores within individuals across repeated assessments, and what we're doing is we're looking at difference scores. The primary unit of analysis for our paired sample test is a difference score, okay? So we're taking score at time 1, score at time 2, we're calculating a difference score. That's the metric that's being examined in our paired sample t-test. Questions on paired sample tests? All right. Hypotheses, our null is that the mean of our difference score in the population is equal to 0. Okay, so we have some population, the mean of a difference score in the population. We don't know what it is. We go through and take a sample. Our null hypothesis is the population of different scores is equal to 0. Our alternate hypothesis, the population of different scores is some non-zero value, right? Just in the larger population, if I took all humans and measured them at time 1 and measured them at time 2, the average of their different scores would be equal to 0. That's what we're testing at our null hypothesis, okay? So again, with our paired sample test, the question we're asking is, do the different scores across assessments in my study, do these differ significantly from 0 enough for me to conclude some non-zero difference in the larger population? So for our data here, our test is going to be the mean of the difference scores, or sort of average at time 1, average at time 2. That's the same, mathematically the same thing, minus the expected difference under the null, which is almost always going to be 0. It doesn't have to be. A much stronger test, you sort of calling your shot. You're saying that I need to have at least a 5-point change in order for this to be meaningful. You would set that for 5, and that will be perfectly fine. But in general, so we put this to 0, and down here we get the standard error of the mean difference. Standard error of the mean difference is the standard deviation of the difference scores over the square root of the sample size. Okay. Now this is where we need to start being careful and thinking clearly about what we're doing here. So let's say we've got a small study, 4 people. We've got assessments at time 1, assessments at time 2, and then we've got our difference scores. Okay. This right here is the stuff that we're using, and when we go through and screen, these difference scores are what we're screening. Okay. Time 1 doesn't matter, time 2 doesn't matter. The only reason time 1 and time 2 scores matter is because this is what's going in and what SPSS is calculating to grab the difference score. Okay. So if we're thinking about assumptions, time 1 could be crazy, skewed, and ridiculous, and time 2 could be crazy, skewed, and ridiculous. But if they're crazy, skewed, and ridiculous at about the same rate, and my change scores all look to be normal, it doesn't matter what time 1 and time 2 look like. What we're actually looking at is this difference score. And what we're doing is we're asking about, sort of looking at the mean and the standard deviation of these different scores here. Okay? Now this starts to become important when we're going through and calculating things. If I calculate the mean at time 1 and the mean at time 2, and I subtract those two things, I get the mean of the difference score, right? There's a lot of, I can get these by subtracting mean 1 and mean 2, that gives me the mean of the difference scores, or I can just take the difference scores, calculate the mean of that. This is going to give me the same number. Okay. Can I take the standard deviation at time 1, standard deviation at time 2, and subtract those two things and get the standard deviation of the difference scores? Absolutely not. That's a completely different thing, right? And so this is where we need to start thinking about when we're reporting things, particularly if I'm wanting to report confidence intervals and things along those lines. Standard deviation and difference score is something that probably should be included. So, any of that look familiar with what we had over here?
Yeah.
Yeah. What is it?
Well, it's just like using the different scores in place of like mean values that you get.
Yeah.
for each example.
And so what are these formulas from?
For the independent samples.
Not the independent sample,
I don't know.
you got it, Sally. What did you say?
The simple.
Single sample, right? So if we want to think about, and so this helps when we get into repeated measures, ANOVA and things along those lines. Our paired sample t-test, all it is just a single sample test with different scores, right? We're just taking these these different scores and we're comparing it against 0, right? At the end of the day, our paired sample test is no different than our single sample t-test. It's just we're using the mean of the different scores, the standard deviation of the different scores. That's all that's going on with this, right? And just would like to point this out because this can be kind of confusing. You think like, oh, it's a paired sample test and we've got time 1 and time 2 and we go say, look at this and look at that. At the end of the day, in the background, all SPSS is doing is just calculating a virtual column of different scores and then just running a single sample test on that column of different scores. Yeah.
So we're assuming that the population mean difference will be 0.
Yep.
So in reality, the T is just the mean difference over the standard error difference. Okay, cool.
Yep. And so remember, because so it looks like we're using 2 different groups or 2 different sets of stuff, right? So we've got time 1 and time 2. But in reality, we're only using 1 set of different scores here, right? And so if we look at, this is my calculation of my standard error, how many sources of error do I have? Just 1, right? Because I've just got, the only thing I'm working with is this column of different scores. Now with our paired sample, or our independent sample test, this is where we have variability in error in sample 1, variability in sample 2, and this is what ends up happening is my standard error functionally gets doubled, right? Because I'm having to deal with error in both of these independent samples. With my paired sample test, and this is what contributes to the power. 1, everybody's serving as their own controls, right? So we get a lot of individual different stuff taken out of the equation. And then 2, in terms of from a mathematical standpoint, when we're calculating our standard error, we've only got 1 source of error. Only source of error is in this different scores here. And so now relative to like a paired sample test, basically in a paired sample test, we're doubling our standard error. And if I double my standard error, what does this do to my test statistic? If I make this denominator twice as big as what it would be, what does this do to my resulting test statistic? Makes it much smaller. And if my test statistic is smaller, it makes it harder to claim statistical significance and all that type of stuff, right? So this is why, at least from a conceptual and mathematical basis, why our paired sample tests are so powerful. People are serving as their own controls, and because we're only working with 1 column of data here, we're not working with independent samples, it's reducing that standard error estimate, okay? Which gives us much, much more powerful tests. Questions on this? Yeah.
What's the likelihood that our mean difference would somehow equate 0 since we're not like squaring?
Oh, these are the mean, well, because these things are sort of independent of one another, right? So we're not, again, if we're calculating variance, right, we're subtracting from the mean value. And so we run out of degrees of freedom there. It has to sum to 0. This is just independent people pre and post. So your different score, unless you're like right on the money and the actual population effect actually is 0, it's not gonna, it's different than calculating variance with your sum of your deviation scores has to sum to 0. This is a little bit different procedure because we're not subtracting the mean from everything. Other questions? That was good. Okay, cool. Assumptions of our paired sample T. Basically, they're the same assumption we have of our single sample T. Our outcome variable is continuous. Sampling distribution of different scores is normal in the population. Data don't contain outliers, and then all of our auxiliary stuff that we would normally expect. There's sort of nothing, sort of other things that we need to account for, that we've got a random sample, we're not fooling around and sort of deciding what our hypotheses are after we've run our data, like that type of thing. So, thinking about effect sizes. Effect sizes get a little bit complicated here because we've got some different options. Once again, just a mean difference score. If I have an outcome that has some sort of inherent intrinsic meaning, just the average of the different scores can be a meaningful metric of effect size, right? If I'm talking about weight or money or something that everybody knows what it is, right? I can say what is the impact of having a PhD on outcome, right? So we look at people with PhDs before and after they got their PhDs in terms of income. It's a terrible study, but we say, oh, it's this many dollars, right? That means something. We sort of kind of know what that's about. So if we're working with a metric that has meaning to it, mean difference scores can work. We can also calculate, sort of, again, Cohen's d in general, sort of generic Cohen's d, is just the mean of the difference scores over our standard deviation estimate. Problem is with the generic is what standard deviation estimate are we going to use as our standardizer, right? That's where we have to start thinking about, okay, what's the best option? Now, in many cases, we can calculate Cohen's d as the mean of the difference over the square root of the average variances. Right? What is this, Chrissy, what is this analogous to?
The pooled variance?
Yeah, it's analogous. Is this the pooled variance, right? The nice thing about our paired sample test is I have to have the same number of people at time 1 and time 2, because if I don't, I can't run the test, right? So I don't have to actually worry about the pool. I can just go through and literally create an average here, okay? Now, the thing to remember is, particularly with our output in SPSS, SPSS is generally giving us standard deviations. The average of the standard deviation is not the same as the square of the average variances. Those two values are not the same thing, okay? So here, if I take the standard deviation at time 1 and time 2, and I take the average of those two things, I add them together and divide it by 2, that value I get for the average standard deviation is not going to be the same thing as I get if I take the variance of time 1 and time 2, average that, and take the square root. The average of the standard deviations, this is wrong. You want to take the variances, average your variances, and then take the square root of that. That's, if you do it the other way, you're going to be off. So again, like anything else in this class, you make an argument, does it make that much of a difference? I don't know, we're doing science, so yeah, kind of, I guess, let's do it right. Again, this is something you want to be careful. You just take those standard deviation estimates, square those, and then average them, and then take the square root of that. I mean, you can try this for yourself. It's mathematically, they're not the same number, right? So you just want to make sure that you're good with that. Okay, so this is basically the analog of Hedges G. We've got our glasses delta. For a lot of what we're doing with our paired sample tests, this is a nice option, because a lot of times we have some baseline starting point that's the whole time 1 thing. So this can be a very, very nice way to go about things. And then we've got other sort of R-squared stuff. You don't have to worry about this. We'll get into that when we get into regression-based things, okay? So this is all pretty much similar to analogous to effect sizes that we've calculated before. But we have a couple of different options that we can use with our repeated measures. We could calculate something that I've sort of labeled here as D of difference scores, okay? What we've got here is the mean of the difference scores over the standard deviation of the difference scores, okay? So different than this, right? This is just looking at the average, the square root of the average variance at time 1 and time 2. And this is just using your standardizer as the standard deviation in your baseline. What we're doing here is we're taking the mean of the difference scores and divided by the standard deviation of the different scores, okay? Now, there are reasons to do this that we'll get into the next lecture, right? The concern is, and again, if we're thinking about all of the whole reason why we're running our paired sample test is that Chris can be all over the map, Siley can be all over the map, but at the end of the day, if you two are changing about at the same rate, how is the standard deviation or the variability in my different scores going to relate to variability at time 1 and variability at time 2?
Same, similarly.
Okay, so how about this? All right, we've got time 1, time 2. Okay. And here's 8, 1, 30, 99, 2. Okay.
Okay.
What's the variability in that set of scores? Massive, right? And I go through and I measure people at time 2, and you get 10, 4, 31, 97, 3. Okay. What's the variability at that look like? Massive, right? But if I look at the difference, right? I've got 2, 3, 1, -2, 1. What's the variability in those scores? Low. Really, really low, okay? And so the concern with using the standard deviation of the difference scores as your standardizer, what's my effect size gonna be for the mean difference across time 1 and time 2 if I use so standard deviation baseline versus standard deviation of the different scores? Anything, CJ? Yeah, so my variability at time 1, what's my variability at time 1?
High.
What's my variability in my different scores? So, okay, so what am I going to get in terms of my effect size if I create this, an effect size using the standard deviation of the different scores as my standardizer versus the standard deviation at time 1?
It'll be a lot lower if you use the difference.
Yeah, right. And so what's going to happen, my standardizer here is going to be much, much smaller than my standardizer if I'm going to use here, right? And so this is the concern with using this as the estimate of your effect size, is it can wildly inflate what the effect, what the effect is looking like, right? Anybody here done any work with like psychophys types of stuff? Okay, what type of psychophys stuff have you worked with?
Heart rate variability, blood pressure.
Okay, any skin conductance type stuff? Okay, well, let's say with some of those things, if I go through and I have just a bunch of random people come in and I'm measuring cortisol, heart rate variability and things like that, where are people gonna fall at time 1? Kind of gonna be all over the place, right? And if I go through and I measure people sort of after a manipulation or something like that, at time 2, there's still a lot of individual differences there, right? But if I go through and I look at the difference score of those, sort of my sort of baseline heart rate and sort of capacity and things like that probably isn't going to change a whole lot from time 1 to time 2. Same thing with anybody else, right? So my dissertation looked at skin conductance stuff. People are all over the map in terms of skin conductance when they come in, just based on sort of characteristics of their skin and sort of things along those lines. Some people are super easy, it's really sweaty. They're easy to get a really high level for that. If they're not, if they got dry skin, it's going to be a lower level, right? But across, if I'm looking at sort of hooking you up time 1 and time 2, at time 1, people are coming in, their sort of skin conductance range from like 1 to 15, right? Coming in at time 2, it's still going to be all over the place. But in terms of looking at their change, everybody's probably going to be changing about at the same level, sort of differences and things like that. And so the concern is if we use a standard deviation of the difference score as our standardizer, the potential for this to wildly inflate our estimate of effect, which we want to be careful of because we already know within the literature our estimates of effect size are probably already really big anyway. Okay. Now when we go through and calculate, working through calculating confidence intervals around our effect sizes, then we're limited to this. We have to do this. But if we're just going through and reporting effect size, we want to go through and take a look. Okay. Now there are some cases, again thinking about treatment stuff, where your standard deviation, your difference scores actually might be quite a bit lower than standard deviation, or if you're using like glasses delta. So let's say we're running an intervention on PTSD, right? We're recruiting people with high levels of PTSD. Everybody's coming in, and everybody kind of got high levels, so we're sort of not a whole lot of variability at baseline. And then we go through and measure it post-treatment, right after everybody's gotten an intervention. What do we know about intervention? It works for some people, it doesn't work for other people, right? And so if I go through and I take a look at my variability at different scores, that can be really big, right? So I've got some people who worked well for, some people who didn't work at all, some people in between. So I could find that variability in my difference scores is actually quite a bit larger than my variability at baseline. This is something I have to go through and take a look at and try and gauge. So what happens to my effect size if I'm using different standardizers, and how am I thinking about that? So this is using standard deviation and difference as your standardizer. You'll also see this equation used some. This is an equation used to estimate power. You probably shouldn't use this to report on an effect size as something that's interpretable. This is something, so this is taking into account your d-value using the average of your variances here and correcting it for the correlation between time 1 and time 2. Again, this is something that we use primarily for power. Shouldn't be using it for reporting effect because this is almost always going to be considerably larger than some of your other stuff. It looks nice on paper, it just doesn't communicate things in sort of the way, practical way we would like to have things communicated. Okay. Questions about any of our options for metrics in terms of effect sizes here?
So it seems like a lot of these are like similar, or at least, so when would you want to use one over the other?
Exactly. So when might we? So we talked about using glasses delta. If I've got like a baseline measurement that looks pretty good, right? I might do that, right? This is going to be your. Honestly, same thing with like Hedges G, and so using standard deviation, the square of your average variances. This is kind of going to be a default. It's kind of
Okay.
like you probably can't go wrong with it. I mean, there's going to be times when this is probably going to be a better estimate than this, or sort of this maybe conveys more meaning than this necessarily, right? But sometimes, and we'll go through in the example we'll work through today, there's one of the outcomes that this is probably going to be arguably the best one or the most meaningful metric to calculate. And then for the second measure, probably average of the square root is probably going to be a better way to go through and think about that. So wanting to think about the methods and what makes the most sense. Again, if we're using standard deviation and difference scores as our standardizer, this is going to happen if we want to calculate a confidence interval around our effect size. We're going to have to use this, right? But if we think about practical interpretations, I can interpret this as, let's say I have an effect size of 0.8, right? And I've calculated it here. I can say it looks like from time 1 to time 2, there's about 0.8 of a standard deviation unit increase in my outcome relative to total variability in the sample. That makes some sense, right? Or I could say here, I've got about 0.8 of a standard deviation increase in outcome relative to the variability at baseline. That makes some sense. Here, I've got about 0.8 of an increase in outcome relative to variability and the difference scores across. So the actual applied interpretation starts to get kind of tricky here because I'm talking about the standard deviation of the difference score, and it kind of starts to fall apart. I know what I know what variability at baseline looks like, and I can talk about variability in terms of the sample as a whole. Talking about variability of the difference scores in terms of thinking about how I'm interpreting this and thinking about some of these metrics. Now, generally, they're all kind of fairly similar, and so it just based on conceptual issues of like, so why would I choose this or the other? And so we'll go through some of those examples of that. Okay. All right. Okay. So our example here. So this is none of you guys know what happened. This is my graduate student based on his thesis. He's out on internship right now, so I took some creative liberties. Again, this is the Disney treatment, but we're saying researchers are interested in the impact of mental imagery on the regulation of subjective anger. Okay, so we run a pilot, and we were looking at the efficacy of mental imagery manipulation. So what we do is we have people come in, ask people 0 to 10 baseline ratings of anger, and then we ask people to imagine a time in which they experience intense feelings of anger. have them do this for a period of 2 minutes, and then have them rate on the same 0 to 10 scale their peak level of anger during that imagery, okay? So we've induced anger, and now we want to see if we can reduce it. So what we do then is say, okay, stop thinking about that angry memory. What I want you to do instead is think about a time when you had, I'm going to ask you to rate your level of anger on a 0 to 10 scale, right? So people are thinking about positive time in their life, so every 20 seconds they're going down through their writing levels of anger every 20 seconds for a period of 2 minutes. And so we're going to say increases in ratings from baseline to peak anger during negative imagery and reductions in subjective anger from the first rating to the final anger rating during positive imagery. We're going to take this as evidence for that our manipulation was successful. Okay. So what we're going to do is open up your paired sample tests here and grab your paired sample screening output sort of here. Okay. So when we're going through and taking a look at our outcomes, what I'm going to do here, I'm going to open up a syntax file. I should analyze descriptive statistics and descriptives. And then my ratings I'm interested in here are initial anger and peak anger, and my anger recovery 1 and recovery 6, right? The other stuff, the other 20 seconds, we're not concerned with that, okay? And what I'm going to do is I'm going to paste that into a syntax file. So this, if I were to run it, and we can run it, this is going to give me sort of mean max range of my ratings that I've collected, okay? Siley, is there anything sort of funky in terms of my ratings that I've collected here? No, it's all 0 to 10, so they're all falling within range, right? What might grab your attention in terms of what we're seeing in this outcome?
Their initial anger is a bit lower.
Okay, so baseline anger is lower. What about the sample size? Anything there?
One of them doesn't have recovery.
Yeah, so it looks like I'm missing at least some scores somewhere in there, right? And so I can take a look at this, but for my paired sample test, is this, Alicia, are these the data that I'm interested in, these scores in terms of screening for my paired sample test? Sally, you're shaking your head, no, why?
Because you want to look at the differences.
Because I want to look at the differences, right? My assumptions are about the distribution of the different scores. So this is a nice way to go through and just make sure that my raw values are falling within line, right? That I don't have anybody putting 11s or 12s or 15s or things like that. But this really isn't what I'm interested in looking at. What I need to do is calculate within SPSS some difference scores. So what I'm going to do is I could go through here, I'll show you how to do it. We go to Analyze, Transform. Go Transform. We can view variable. And I'm going to create a new variable, and I'm going to call it difference. Okay? And anger difference is going to be equal to peak anger minus initial anger. Okay? Now, when we're calculating difference scores, I'm going to encourage you to always subtract the first score from the last score. So we're going to enter peak anger, which is sort of my endpoint, minus my initial point. What this is going to do is it's going to make all the signs on these sort of match which direction they're going, right? So if I take peak anger and subtract baseline anger, and my manipulation is working, should I get scores that are positive or negative? Positive, right? And that's indicating increases in anger. Now I can subtract, I can take the baseline anger and subtract it from peak anger, and it's going to give me the same. It doesn't make any difference. But now, increases in anger are going to be indicated by negative value. It's kind of hard to keep track of in your head. So what we're going to do is we're going to subtract peak anger from initial anger, and I'm going to hit paste. Okay? And this is just your basic SPSS syntax for generating new variables. So I'm gonna go do that, but then because I don't like running through pull down stuff all the time, I'm gonna copy that and I'm just gonna put down, and I'm gonna create another variable. And what am I gonna call this? I'm gonna call recovery difference. And what I'm gonna do is I'm gonna take sub-anger 6, that's my last rating. Paste that in there. I'm going to take sub-anger 1. Paste that in there. Okay. So what I'm going to do is I've got 2 different tests, right? I want to run a test on my anger manipulation and on my positive energy manipulation. Okay. And so what I'm going to do is I need to have 2 different scores that I'm running here. So I'm going to go through, highlight this, run that. I take a look, we'll see I've got anger difference in my anger scores for my anger manipulation and then my positive imagery thing right here. Okay. So we've gone through and we found that all of our values are within plausible range, right? So that's good. Other thing we might want to do though is we want to take a look at missing scores. Now this is easy because it's a small data set. I can see that if I sort ascending anger difference, looks like we've got all values there. If I sort recovery difference, looks like I'm missing the score for participant number 18, right? Anytime you're going through and running, just as a trick for SPSS, if I've got a number of different outcomes I'm going to be looking at and want to see what's my data, what's my set look like with all data, my complete data set, if you just run a compute statement and say this plus this plus this plus this plus this, anything that's missing a value won't come up with a score. It's a quick and easy way to go through and figure out where my missing values are, okay? So here we see that participant number 18 is, looks like they're missing anger recovery scores, right? So I want to mark that down, indicate what they were missing. But at the end of the day, I want to just look at my data with full scores here. So I'm going to go through, after I mark down that this person is missing data and why, I'm going to go through, oops, and clear that person out. Okay. Everything else is looking good. I've got 42 people, so I'm feeling pretty good about this situation. Questions about what we've done up to this point? Okay.
Would we not just be interested in just marking your data as missing? That way we can still look at their other scores? Or is it just, I mean, I guess it depends.
Yeah. And this is kind of a philosophical difference. For me personally, if I'm going to go through and present a bunch of different analyses, my preference is to have the same set for this analysis versus this analysis, because for me it just makes it sort of more comparable. Now in this case, could we run manipulation on the anger induction with the people who have scores for that, and then the recovery on the people who have scores for that? Probably wouldn't make it. It's one person. It's not going to make a huge difference. For this, for our stuff, we'll just work with full data. But if you wanted to go through and do that, the only thing it does is then it kind of increases the burden on you to describe what people were in what sample and how and when and things along those lines. Okay? It just kind of makes it a little bit more difficult. But if I have a lot of missingness across different things, and that might, if I'm just looking at the complete data and it starts to impact my sample size a great deal, then I might sort of make an argument for why I'm looking at different subsets of the sample for different analyses. But again, that's sort of one of the justification for that. All right, so we've got scores for our complete set here. So what I'm going to do now is going to go through, go to Analyze, Descriptives, and get rid of all these folks. I don't care about them. And I'm just going to go through and look at anger difference and recovery difference. I'm going to go to Options, ask for skew and kurtosis values, and I'm going to go through and I'm going to hit Save Standardized Values as Variables. Tomorrow, why am I saving standardized variables, standardized values? Yeah, and what are the z-scores going to tell me? Standard deviation, which is leading to extreme values, right? So I want to see if I've got someone who's way out of bounds with stuff, okay? So I'm gonna go through and I'm gonna hit paste. And then I can go through and just run this. Okay. So, CJ, any concerns, or taking a look at my descriptives table here, anything that's sort of making me concerned about stuff? Yeah, I don't think so either, right? Things are looking all right. For my differences in my anger scores, my skew is close to 0. My kurtosis, about -0.5, suggests that I might have kind of a boxy distribution, but this is well within the bounds of stuff that we would consider not problematic. For my anger recovery, it looks like some negative skew, -0.4, a little bit of negative kurtosis, but all of this stuff is falling well within the boundaries of things that would be expected, so I'm not too concerned about anything here. So there's nothing in terms of my indices of skew and kurtosis that would make me concerned that, hey, maybe we've got something that could produce a violation of sort of looking at the normality normality of the sampling distribution, right? Again, because remember that our actual assumption isn't about the data that I'm looking at. It's about the distribution of sample means, right? And now if we've got small samples and way distributions that are way out of whack, then that's something that we have to worry about. Here I've got a sample of 43. Is sample 43 a big sample? Yeah, I mean, big enough, you know, depends on what I'm looking for a paired sample test. Sample 43 oftentimes give you enough power to, these are just really powerful studies, right? If I got 43 people in a pilot, that's actually a pretty good pilot, right? So now is it a huge sample? No, it's not a huge sample, right? But it's probably enough to do the trick for what we're wanting to do, right? And again, if we think about the distribution of sampling means, right? What are the two circumstances which the distribution of sample means starts to approximate normality very quickly? Sample size above 30, and what else? Yeah, population distribution is normal. Now, I don't know too much about whether I don't know if the population of different scores fall in my manipulation is normal. Might be, I don't know. But I've got reasonable cell size here, so it really doesn't matter, right? It could be really actually pretty skewed. Still with this sample, so distribution sample means it's gonna hit normality pretty quickly. Right? So things are looking good here. So let's go up and go to Analyze, go back to Descriptives, and drop down to Explore. Here, we're going to go through and once again ask for anger recovery, anger difference, or excuse me, anger difference and recovery difference. And what I'm going to do is I'm going to take subject and drop it in down in the label cases by. And I don't think we're going to hit anything, but eventually we're going to hit some stuff where we've got weird values kind of falling outside bounds. What this will do is it'll start labeling in our box plot values that are falling beyond 1.5 times in the quartile range. It'll start labeling them with subject numbers to help us identify. If you don't put anything in there, it'll put case numbers by there, and that you can be confused by that stuff. So, I'm going to hit plots, request histograms. I'll turn off assembly for this time here. I'm going to hit paste. Think about it for a while. Yikes. Good work, University of Wyoming. Computer power, awesome. Okay, here's anger differences, okay? Am I seeing differences? So anything, Alicia, what am I seeing in this histogram?
It looks mostly normal.
Looks mostly normal, right? And so, is there anything that looks problematic or concerning with this? And so this is when it starts to become important to think about what our data are actually saying. And so I agree. I think that's a notable thing I would mark down and take note of in the screening thing. It's not problematic. But if remember, this is anger difference. What does this kind of peak at 8 mean within the context of what we're measuring?
So it looks like the anger went down and then it went back up.
Okay, so it's just one difference, right? So if we're taking peak anger minus initial anger, right? What does the value of 8 tell us for these people in terms of our manipulation? What's anger doing for these folks? We're taking initial anger and subtracting sort of where they were at baseline. At 0 to 10. So I've got to say, at the start, my anger's at 1, and when I finish, my anger's at 9. I take 9 minus 1, what does that give me? 8. What does that tell me about my anger? It's gone up, right? So what we're seeing here is that we've got 4, sort of a good portion of individuals, like we're seeing an 8-unit increase in anger. Am I excited about this in terms of sort of thinking about efficacy of my manipulation? Absolutely. I kind of like that, right? It's suggesting that people have gotten from baseline to sort of where we finish up. We've seen an increase in anger from baseline to peak. Now we've got some people down here. What does 0 mean? No change, right? These are people who didn't change. So these are people who my manipulation weren't successful for. And then people kind of, it looks like my sort of median point here is about 4-ish, right? Or maybe it's a little bit higher, right? But overall, so if I'm looking at this in terms of distributions, not concerned about that. But what I might note, just based on here, is that, and this is why we go through and graphically look at our data to try and sort of draw some inferences about what's going on. If I'm looking at this, it's kind of normal, but it looks like at least for a substantial, or for a subset of people, they're getting a considerable bump in anger, and then sort of some more moderate stuff there. So this is good for me to, I'm excited about this, right? If we go down through and take a look at anger differences in our box plot, tomorrow, anything interesting going on here? No, not really. No values falling out beyond 1.5 times interquartile range. Looks like I've got a median value of 4, a max of 8, a minimum of 0. Interquartile range running from about 3 to 6. So, but this is a symmetrical. I would identify that box plot as sort of symmetrical, sort of otherwise unremarkable. Sort of things are looking okay there. All right. So what about this histogram? Anything concerning with this histogram? And so remember, this is recovery. So we're taking over the course of positive imagery, we're taking final anger ratings and subtracting them from where we started.
So it seems like a lot of people went back to their baseline.
Okay, so I don't know if it's back to baseline, but we're seeing reductions, right? And so this is good. A lot of people did. What did most people do over the course of my positive imagery manipulation? What did most people experience in terms of change? Fair enough. Fair enough. I think probably if we took this end of the distribution, we'd say reducing some. What's the modal response? Do you have it?
Probably the response to your intervention.
0, right? So the modal score here is I've got the most frequent response to this in terms of individual was people didn't change at all, right? So from my if I take my final rating from my initial rating, people were rating it the same, right? Chris, what's going on down here at this end of the distribution?
Those are people whose anger went up after the intervention.
Yeah, so over the course of 2 minutes of positive imagery, we've got it's like 5 people who reported an actual increase in anger, right? What do I make of that?
It's bad.
Yeah, I don't know. What I might
didn't help for those people.
Yeah, what I might do is go through and want to check my records to see, did someone get something entered wrong, right? To make sure that so that we didn't have anything going on here, or someone switched anything around. But it's quite possible if you're in my lab, and I'm telling you to think about something positive, and every 20 seconds I have you write down your level of anger. Maybe for some people that's irritating, and so they actually sort of get more aggravated, right? So again, if I'm going through and I'm sort of looking at this histogram, right, I might say, well, it looks relatively normal, some negative skew going on. We've got at least one person who's reporting an increase, or sort of a small number of people reporting an increase. We've got one person who's fallen away from the larger distribution of scores. But overall, that's just my, in terms of my assumptions. Do I have anything too concerning going on here? No, right? So nothing that would say, oh, we can't do it paired sample t-tests, right? And then here, my box plot, again, looking all right. I've got a median value of, looks like a 1, right? So everything's sort of looking all right, so min max and things along those lines. So my distributions, am I okay with my distributions? Yeah. But the thing I want to really bring home here is when we're going through and looking at our distributions, it shouldn't just be to look and see if things are crazy skewed or out of bounds or things like that. If we're doing, and it's hard to care about examples in class or problem set examples, but when you're in your own research and you're actually looking at your own data, think about what these scores mean, right? Sort of practically, what is this telling me about my manipulation here, right? I might start to want to think about not just getting an idea of whether or not my manipulation is working. Is it increasing or decreasing anger as I had intended? So what's going on? What's the variability? Because this is where we can start to see, if we're seeing weird stuff go on that we didn't expect, that should trigger back, oh, I need to go through check records, think about what I'm doing. Yeah, it's working for, just based on these data, am I more excited about my anger induction or my positive mood induction? My anger induction looks like it's considerably more effective than my positive mood induction, right? And this is the thing that we don't need to run statistical tests on. We can just look at our data graphically and start to develop a much, much more rich understanding of what's going on. This is the thing, when you guys go into theses defenses, dissertation defenses, there's no one in that room that should know more about your data than you, right? I go, well, what about this, that, and the other thing? And then making that, shut it, grandpa, like, this is what's going on with this, right? Like, I actually looked at that, and it looks like sort of reasonable, like, really, you might expect that, but really, we didn't find anybody who had the opposite thing, right? Or, like, oh, is this actually a thing? Like, well, I don't know, on average, sort of really the positive manipulation, sort of modal response was nothing at all. But the majority of people did report some reduction here, and that's kind of what's going on. We did have a couple people that increased in terms of anger, but do we keep those people in my analyses? I sure would, right? Because otherwise, I'm like, oh, these are the people that the manipulation didn't work for, so like those people don't count, right? Well, some people that manipulation's not going to work for. I can't just kick out people who didn't do what I wanted them to do, right? So wanting to think carefully about that. All right. So the last thing I'm going to do is I'm going to go through and take a look at my z-scores here. And so I'm just going to go through and just add a z to the front of each one of those variables, because that's what SPSS labels. So I've now got Zanger and this is recovery, which is exciting. I'm going to go through and pull skew kurtosis off of this. They don't need to give me skew kurtosis values. Go through, I like that, run it. Okay. So any concerns with extreme values in these data? No. Right. I've got at most for my anger induction, someone falling a little over 2 standard deviations below the mean. So these are just going to be people who didn't respond much to the anger imagery. For my anger recovery, got anywhere from about 2.5 standard deviations below to 2 above, right? Again, at this stage of the game, this should give us nothing interesting above and beyond what we've already gone through and seen with our distributions or with our histograms and box plots and things along those lines. But as we start to get into bigger data sets, where we get values that are sort of starting to fall out, we can have values that fall or detached from the rest of the distribution that are still probably reasonable. It's just nice to be able to give someone a quantitative metric to say, this case was an extreme value. An extreme value is specifically by this much. This is what we decided to do with it. We decided to leave it and sort of smooth it, something along those lines. Okay. All right. So, in terms of conclusions, right? Again, if you want to grab the screening summary for your paired sample tests here, right? So we found case number 18, missing values for subanger 1 to 6, right? So again, who knows? We have in experimental studies, if you've done experimental studies, things go wacky all the time with new stuff, right? So I'm probably not too concerned about that. No evidence of problematic values. We've got 42 people in the reduced set, talking a little bit about the distributions for difference in anger, or during the anger induction, the positive imagery, outlier stuff. Recommendation, pretty simple, straightforward for this. Everything's looking pretty good. But please do, for this next set, use this as your, I won't often give you templates, but use this as your template. This ends up being, I know that I gave you in these examples sort of a paragraph version of the screening write-up. Please don't do that because it's hard to go through. And for us to make sure that you've got everything, it's going to be harder, probably more complicated for you to write that up anyway. What we want to do is just have you go through and bullet sort of different things that you're finding here, and then just write a very brief summary there at the end about stuff that came up or things that we might want to be attuned to as we're moving forward with things. All right, questions on any of the screening procedures here? Awesome, okay, cool. So what we're gonna do now, quick and easy, we're gonna go to Analyze, Compare Means, we're gonna go to Paired Sample T-Test. Quick. And what SPSS will do is it's just going to pair things up. So I'm going to go put peak anger first and subtract that from initial anger. And I'm going to go recovery rating 6, subtract recovery rating 1. Just make sure that's lined up. And then we go through and paste. We can see here, so I got, for my initial ratings, I got peak and sub-anger 6 with anger start and sub-anger 1. Go through, make sure that that's looking good. Run this. And here's my t-test, right? Again, the screening is going to take 4 times as long as the actual running of the tests, but that's just how applied data analysis goes. If we look at our paired sample, our descriptive statistics up here, again, 42, 42, okay, that's looking good. I've got peak and initial, I've got recovery 1. Look at that, make sure that these are actually making the pairs that you're expecting it to make. We've got sample sizes, mean standard deviations, right? SPSS will give you the correlations between time 1 and time 2. And so here it looks for a much stronger correlation between the final anger rating and the initial anger rating during the imagery manipulation than across the anger induction, which is kind of interesting. Again, these are all things that tell you things about your data and what the manipulation is doing, things along those lines. And then down here we get our paired sample tests. Okay. Nick, tell me what's going on with my anger induction, my initial anger induction.
Yeah, so we're seeing about a 4.5 increase from initial to post. There. The T statistic is pretty high, and that's also reflected by the p-value, but SPSS doesn't report past that, so
yeah.
You can look at it further, but there's, for the confidence interval, it's about 4 to 5, so about a 4-point minimum increase to about 5 at most.
Yeah. So we didn't specify what was a meaningful increase in anger, but given sort of our ratings, or 0 to 10 rating, and so if I'm just asking people for a period of 2 minutes to think about something, a time in which they were wrong, or in which they were angry, or things along those lines, based on our data, at the low end, we're looking at close to a 4-point increase in subjective anger, sort of as a consequence of this. I would count that as good, right? And that's at the low end, right? Our best guess, looking about a 4.5-point increase, at most a 5. This is all actually pretty tight in here, right? So I'm actually feeling like this is giving me a good bead on 4 people, at least university undergraduates coming in, so whether or not this is going to be an effective way to get people to experience some subjective feelings of anger. Okay? One thing I want to make a note of is a small correction, but it's something that comes up a lot, but something you want to be careful of in terms of your write-up. Oftentimes, and I think this is just a function of people trying to knit information together in a way that sort of flows in the English language. But sometimes people will say, so we found sort of p-value less than whatever, and that was statistically significant. In addition, the confidence interval didn't contain the null value, so then we also, that's further evidence of this being a non-zero fact. Okay, what's my beef with that presentation?
It's yes or no. Either contains it or doesn't.
It either contains it or it doesn't. Yeah. But what's the problem with me saying that this provides further evidence against the null?
It's kind of just a byproduct of what.
Yeah.
the reporting is.
It's all the same thing, right? If I have a confidence interval that contains the null and I have a p-value that's less than 0.05, something's gone something's gone wrong, right? And so the confidence interval is just a different expression of your hypothesis test. As long as you're using a 95% confidence interval and alpha of 0.05, it's not giving you more information or additional information, right? It's not that I can run into a situation where I reject the null with my t-test, but my confidence interval contains the null value, and then I'm like, which one do I believe? So it's not. So what I want you to know is it's not additional information, or it's not further evidence. It's just a different look at the same thing, right? And so again, what I would say is that yeah, we've got a pretty tight confidence interval here, suggesting anywhere from about a 4 to 5 point increase in terms of subjective anger as a consequence of anger imagery. It's associated. That's a massive test. That's a ridiculous test statistic, right? Basically, if we go through and we calculate, and I did here, the S value associated with this. So my S value for peak anger is 54, and my base factor bound is equal to 1.39 times 10 to the 14th. Okay. Yikes. These data are basically assuming that this anger manipulation actually causes no change in anger in the population. These data are functionally impossible, right? This would be the same thing. So evidence against the null in this case would be similar to getting 54 consecutive heads on a fair coin. That doesn't happen, right? The likelihood of the alternate relative to the null is 1.39 times 10 to the 14th. It is just functionally impossible, right? So we have very, very clear thinking of the p-value. I don't even know what the p-value is. It's something ridiculous, right? So we have very, very strong evidence against the null based on this data, right? If we go through what might we want to do in terms of calculating an effect size, what would be a good option for an effect size estimate for our anger induction? What do you think, Chris?
Would code C be a good one?
What's
Or
that?
is this where we want to use glasses delta?
What do you think? What would be the strengths of glass delta?
You could look at the variability at the baseline.
Yeah, right. In this case, we've got a pretty straightforward baseline, right? We just had people coming in, asking how angry they are right now. That's a nice baseline, a nice control to base our variability on, right? So if I want to go look at glasses delta is equal to, and this is nice because I can just pull these values straight from my output, right? So the mean difference is 4.452. 4.452. over. The standard deviation of initial anger is 1.667. Gives me glasses delta of 2.671. Alicia, can you give me a practical interpretation of that effect size? It is very large, yeah. How would we to make how might we communicate this in terms of sort of making a practical or a conceptual interpretation? Someone help her out? Chris, yeah.
Changes to 0.6 standard deviations.
Yeah.
From baseline to when you measure points of anger.
Yeah, right. So basically, based on these data, what we're seeing is about 2 2/3 of standard deviation increase in subjective anger relative to variability at baseline. That's massive, right? So that's really, really big. And so again, if we're thinking about effect sizes in terms of standard deviation, even increasing, a decrease, difference, and things like that, that's a really nice way, because I know what a standard deviation increase or decrease is. I know what 2 standard deviation increase and decreases is, right? It's a nice way to go through and start communicating things in sort of meaningful metrics, okay? So overall, even this pilot, sort of modest pilot, it's a nice sized pilot, it's only 40 people, incredible evidence that yes, this manipulation, at least for the population of University of Wyoming undergraduates, is fairly effective in getting people worked up, right? What about our, Christy, what about our second test here? What are we seeing there, man?
So it seems like the anchor is reducing for most people, since the mean is by 1.5-ish points. And it seems like any value between 2.3 or -2.3 and -0.9 difference between those two would be reasonable. Our p-value seems like it's well below 0.000. So that we have some evidence that our treatment reduces the anger from recovery 1 to recovery 6.
Okay, perfect, right? Well done. So on average, it looks like over this 2-minute period of positive emotional imagery, after we got people worked up, right? After we get people cranked up, and then ask them to go through and sort of think about a positive time, right? What's the effect of this positive emotional imagery? Well, on average, based on these data, it looks like we've got about a little over 1.5 point reduction in subjective anger on that 0 to 10 scale. Based on the data that we've collected, estimates for the population for anybody anywhere from about a 1 to a little over a 2 point reduction would be compatible with the data that we've collected, right? 1 point reduction in subjective anger for just by thinking about something positive. It looks like it's sometimes easier for us to get cranked up with negative emotion than easier to come back down from positive emotion. So even at the low end, I would still think sort of on average, looks like it's not doing nothing, right? If I'm trying to get the needle to move on subjective experience, it looks like it's doing that okay, right? If I, S value here is 16, my base factor, that's huge, right? So we're still seeing, based on our data, sort of compelling evidence for the alternative relative to the null, right? So this is still strong evidence, not as strong as evidence for our anger reduction, but it's still decent sized, right? What about, what might be a reasonable option for an effect size here? Yeah, what do you think?
Let's see.
Yeah, Cohen Z. And why might you shy away, Chris, from glasses delta in this example?
Because you're not really getting control, like or a trait level of anger. You're somewhere in the manipulation.
Yeah, I would say so. That right here, we're we're getting that initial rating after we've already got people kind of all cranked up, so we've already kind of done something to them. And then at the end, that's just kind of where, so we don't have a really good kind of baseline here, right? And so what I might do, probably just go with a Cohen's D here. So if I'm looking at average of the variance, right? Let's say plus 2.58, 3 squared over 2. It's going to be 5.682, which gives me a standardizer of 2.34. Okay. So again, remember that I'm taking the average of the variances here, and so I need to go through and I need to calculate, get to my variances first, take the average of that, and then I'm going to get an average variance, then take the square root of that to get my average of the square root of my average variances. So Chris, let's see, you got a calculator. Just take 2.166 and 2.583 and divide those two things by 2 and tell me what you get.
2.166 and 2.583 divided by 2.
Yeah, just divide by 2.
Oh,
Just take the average of standard deviations.
Okay, got it. To show those different there. And then we got 2.375.
0.375. Okay. So in this case, it's not a huge difference, right? But we're working with fairly small numbers and things like that. As these variances start to get more and more, right? We're squaring these, and we square a large amount of the numbers, it gets bigger and bigger. These two things can start to become very different numbers, right? And so wanting to make sure within the context of what we're doing that we're using the correct, we're taking the average of the variances and then taking the square root of that to get my standardizer. Okay? So if I do that, I've got D is going to be equal to negative 1.643. Take that over 2.384. It's going to give me an effect size of 0.68. Okay. So again, if I'm thinking about this effect size relative to that effect size, you kind of got a 90-day difference, right? But this is still a very respectable effect size. It's falling in that medium to large range, right? For a pretty quick, simple manipulation to try and bring people down from anger. Just imagining something positive is fair enough. It's doing what it's supposed to do. It's not as powerful a manipulation as my anger reduction, but it's still, I would take this as evidence of my manipulation is doing generally what I would expect it to do. Not for everybody, not as big, but for both of these, I would probably claim success on both of these in terms of a pilot moving forward with the study. All right, questions about any of this stuff? All right. Okay. So this is quick. This is what things look like in SPSS. We just went through all that. Stata, this is just t-test. My one measure equals my other measure. Goes through, gives me all this stuff. Pretty easy and straightforward with this. Here's my difference scores, my t-test, my two-tailed hypotheses, or my two-tailed test here in the center. So all the same stuff that we've done before, just a slightly different output. Okay. Our write-up, okay, go through and take a look. And again, this is just taking some of the things we've put together and trying to go through. Here, I've gone through and actually given actual p-values. Again, I don't know if this will fly ever in terms of publications, but again, if we're thinking about p-values as a continuous measure of evidence against the null, a difference between p equals 0.001 and p equals 7.12 times 10 to the negative 17th. Those are very, very different things, right? And so just trying to communicate this in a way that communicates sort of the magnitude of difference in strength of evidence. Going down to talking about confidence intervals, point estimates, and things along those lines. So do go through and take a look, read through these carefully in terms of thinking about, what can I do? How might I go through and structure and incorporate information that I've gathered and sort of make some conclusions about the research question at hand. Okay. Again, like what I don't want is like a cut and paste and fill in the blank of this stuff. But hopefully this, again, I don't have rights on sort of some of this language, but hopefully just trying to give you a way to sort of think about things and sort of use them to develop some of these, and hopefully they're a little bit different from one thing to the next. So this might look like for a pub. You can go through, take a look at that. So our paired sample tests, okay. Zach Williams said one time, said repeated measures are pretty damn slick, and I would agree. I think they are. He gave me an updated version of the photo there. These are, when you're thinking about your theses, your dissertations, if you can use a repeated measure design, do so. They're just so much more powerful and able to detect things. They're nice because they can start to go through and incorporate things that we're interested in looking at. They're more efficient. They result in a reduction of our error variance. Our standard errors go down, and it ends up being much, much more powerful than our between sample tests. But we can't use these all the time, okay? If there are time-related factors, time-related confounds that would go through and screw with this, then we can't use it. If there's practice effects, I can't give you the same test 2 times and then say, oh, look at that, you did better the second time because of my manipulation. Well, you already did it once, so you already kind of knew things, right? I can't, sort of, Kyle's class, right? They think about, I can't tell you to forget cognitive therapy and not do that anymore, right? So that starts to become difficult. If we've got order effects, right? If the order in which you do certain things start to impact stuff, we can counterbalance sometimes, but these are the types of things that start to become a confound. So we can't use our repeated measures all the time, but if we can, should be looking at that as a way to go through and maximize the power of our tests. Okay. So for our t-tests, we've got our single sample test, got our independent sample test, got our paired sample test. Want to be feel like you have that under control, knowing which situations you use which tests. Here's just appendix for SATA and SPSS, and that's that. Okay. Three weeks on friggin' t-tests, but it's the basis for our means-based comparisons. If you're strong on this now, when we get into contrasts and post hocs and things along those lines, you'll be feeling much better with this stuff. Okay. Okay, yeah. Just run through the first couple of slides here to get stuff out of the way. We're going to go through and start jumping into power and confidence intervals around effect sizes. As we've gone through all of this stuff, we've primarily been concerned with controlling our type 1 error, okay? Someone remind me what type 1 error is. What is the error we're making with the type 1 error? Chris?
It's okay, hold on. We reject it, but something is actually there. Or wait, no, hold on. We reject it, but something's not actually there.
Yes, exactly, right? We're claiming an effect that isn't actually there in the population, right? And so the concern is that I'm taking credit for something that I didn't do, that I didn't demonstrate, right? In our hypothesis test, this is controlled by alpha, or where we set our alpha. We're very, very much controlled with, or concerned with controlling this type 1 error. We don't want to say something's there if it's not. But what we tend to do is not be so concerned with our type 2 error. What are our type 2 errors?
We don't find something, but there's something actually there.
Exactly, right? It's there to be found. I just didn't find enough evidence to claim support for it, right? Why do you think we're less concerned about this? Because I'm a selfish researcher and I don't want you to get anything you didn't deserve.
Well, finding type 1 error can be problematic if we think something's there and we're trying it out, but it's not there. So if we have a treatment, for example, and we think it's effective, but it's not, that could be, people using that treatment will create problems.
Yeah, right. So this is part of the idea, is that not wanting the idea is being conservative, right? Not leading science to start chasing things that aren't actually there, right? But we could make an argument that the type 2 errors are just as bad, right? If I have a treatment that's useful and I don't find that it is, and then say, okay, well, we're not doing that anymore, then that starts to become kind of problematic, right? And when we look at people within different like biomedical sciences and things like that, talking about adjusting, so what is my risk? What are the consequences of me making a type 1 or type 2 error, right? If I've got a medication that has really, really intense side effects, it's dangerous, right? But it could be helpful. I might crank down that alpha error, right? So I want it to be like 0.001, right? Like if we're gonna say that this is a thing to do, I wanna make really sure that whatever we've got is effective given the risks. Or this is a thing that has 0 risks, right? It could be beneficial. Maybe sort of being a little bit lighter in terms of moving forward with stuff, right? But we often don't think about sort of the risks and benefits of type 1, type 2 error. The inherent structure of our null hypothesis testing is focused on this type 1 error, right? The whole null hypothesis testing endeavor is focused on, does my data, assuming that the null is true, do my data fall beyond sort of these tails, right? And so the whole thing is kind of based around this type 1 error. And then also we've had difficulties calculating type 2 error. We're going to go through and we're going to use some tools that have started to become available within the past decade or so, but with computing power, calculating type 2 error starts to get more difficult. And so historically it's been a hard time to go through and do stuff. Type 2 errors also make us sad, right? Because it makes us say, all right, Chris has got an amazing idea for a thesis, right? You do though, let's say you do. Like you got this really cool idea, right? You want to go through and do this, like I've got this whole design, right? What's the likelihood of that being a thing but me not finding it? If we go through and start running power analyses, you say, oh, I could do this. It means I have to have 900 people with eating pathology in order to adequately power this and able to have a reasonable likelihood of detecting this thing that I think this makes me very sad, right? And so as a consequence, it's easier just to ignore it and say, oh, well, Nick et al. Ran 50 people, so my sample of 50 would probably be just fine, right? Failing to recognize that Nick et al. Probably wildly overestimated the thing and maybe a fringe result, and you basing your study on the same number of people that Nick did is destined to failure, right? Like you're buying a lottery ticket, right? So this is where we get into questions about power. Think about power as being the long-term probability of rejecting the null given a particular effect size, alpha level, and sample size. Okay. What we're wanting to do with these analyses is look at the expected power of a planned study prior to the collection of data, right? So Siley says, okay, I'm looking at an effect size of about d equal 0.5, my alpha is 0.05, and I've got 60 people that I'm planning to collect for this. What's the power, assuming that my effect size is accurate, what's the power of my test to detect this effect based on my planned sample of 60? Or this is the effect size I'm looking at, this is my alpha level, how many people do I need to achieve power of 0.8 sort of moving forward with this, right? This is arguably sort of really sort of well, it's not arguably, it is sort of the most appropriate use of our power analyses, although we'll talk about sort of other things we'll start trying to do, okay? Our power analyses, as we work through this stuff, it's not an exact science, right? In general, when we're working with our estimates, we're just really trying to get insights for, given the data that I've planned and the study that I want to conduct, am I closer to something that's reasonably powered or something that's not even close to anything being powered, so that has zero chance of this? Okay. Any ideas on what makes it so difficult to conduct power analyses sort of any type of precision.
It's hard to predict the effect size, especially if you're like, I think this will work.
Yeah, yeah. And I think this will work. If you have a good conceptual reason for why that might work, that's awesome. That's what research is based on, right? But if no one's ever done it before, you getting a reasonable estimate of the effect might be impossible because no one's ever done it before. I don't know what the effect size is, right? Or Tamara wants to do this, and she's gone through and taken a look at the existing literature, doing the best thing we can to try and get a reasonable estimate of this effect, right? But no one's really actually done the thing that you want to do, right? And the reason you want to do it is because you think there are reasons why these data are not so great, but no one's done it, right? So you've got something that looks close, but not exactly what you want to do, so that's difficult. They've used different measures, they're using a different population, they're using a different design, and all that starts to impact the effect that you're going to be looking at, so it starts to become really, really hard, right? And so even if, with the improvements in our calculation, we can very precisely estimate power if we have a strong estimate of the population effect, well, basically that's it. Like, that's the crucial thing that we need. But we also know that our existing literature, effect sizes in existing literature are also probably too big because the things that have gotten published probably have overestimates, not necessarily due to investigators' issues, but just because I happen to get something that overestimated the effect, right? And so it starts to become very, very hard, right? And so it's sort of semi-arbitrary, but we tend to have power related as 0.80 serving as our standard accepted power. If we get less than 0.8, right, this is problematic because we were saying that we have an unacceptable risk of type 1 error. Right?
It's from Star Wars.
We'd have too much power. We could have abuses of power, right? We have too much power, right? So we've got inefficient uses of resources. Siley wants to go through, and you say you want to go through and look at this thing, and you've got a really nice repeated measures test, and you actually only need 30 people in order to have an estimate of effect, or sort of an adequately powered test. You go through and you collect 100 people. You didn't need to collect 100 people. That's not a good use of your resources. You could be doing other things, particularly if running people through that test is stressful for them in any sort of way, right? You're unnecessarily putting people through things, right? And then also, if I go through and I decide I want to test something and I've got 100,000 people in my sample, what am I going to be able to do regardless of whatever my thing is? I can claim statistical significance on anything, right? Because I've got that many people. I've got a massively, massively overpowered test. And so even things that are trivially small, so things that don't make any real difference, right? I found, and I'm claiming statistical significance for a correlation of 0.005, right? And in my sample of 10,000, that comes up as not 0, right? But is that a correlation that's meaningful or has any practical utility for anything? Probably not, right? And so we can get, the issue is far more concerns with things being underpowered, but we also need to be aware of things that are overpowered as well. People claiming statistical significance when absolutely anything they would have done would have come up as statistically significant. Too much power, too much power. All right, we'll leave it at that. Jump into next time empirical. What's that? You want to keep going? We can do it. We can do it.
It's a Star Wars thing.
But yeah, so we're slightly ahead of schedule. We're good, but I don't know. Oftentimes I end up, in the past, I said, okay, and there's also paired sample tests. So here's a screencast video. Figure it out, which is not, doesn't make me happy. Doesn't make other people happy. So we're in a good spot with this. So if you haven't already, make sure that you get an early start on this next set. This will likely